So just to add to a little bit, so I do have this interesting or different background. So just that, computer science is much more than math and programming. I do have this fine arts background, and I bring a lot of that to the kind of research I do, and actually to a lot of the teaching that I do today. And today's lecture, the lecture I'm giving, has aspects of this as well. So let's just, before I get to the really crazy demo that we're going to see later on, let's just think about what a computer is, the term computer. So what is a computer? I thought someone would shout something out. A hunk of, a what? No, a thing, a machine. Is it maybe something like this, right? Is this a computer, right? Does anyone, it's got a bunch of wires, there's a CPU, you can point at the RAM. Fair enough, that's a computer. Now, are you paying attention in your computer science classes? What's that? What's it? Someone said it. But you said it, you say von Neumann machine? I thought you said that. Okay, he might have said that. It's a von Neumann machine, right? So it's a computer is basically these essential pieces, like there's some RAM and there's a processor, these basic little pieces. That's what a computer is. What about this? I don't know if you've seen this yet. Can anyone take a guess? A Turing machine. Whoa, yeah, okay. Anyone heard of Alan Turing? There's a movie. Okay, so a Turing machine is this amazing mathematical model of what a computer is. And a computer basically comes down to, believe it or not, inside every one of your iPhones is a long tape with a bunch of ones and zeros and a head that moves, no, not quite. But essentially, every computer can be modeled in this way with a tape of ones and zeros and a head with a CPU that makes decisions based on the ones and zeros. And you can play, Tetris or Minecraft on that, no problem. There's a couple details. But if I went, so this is how we, as computer scientists define computers. But if you went and you asked someone in 1971, let's say, what is a computer? They'd actually draw you something that looks actually a lot like that von Neumann machine. They would draw you one of those giant rooms of a bunch of blinking lights. There'd be some big tape reels up in the top. That's your RAM. You can actually see the registers, the CPU. The computer is very physical. Like all the parts are kind of on the outside back then. If you ask someone in about, let's say, 1988, what a computer is, they would draw something like that. There's a big difference that's happened between this, and a big difference from those examples that I just talked about earlier, that a computer, people now think of a computer not so much as how computer scientists think about it, with a bunch of RAM and a CPU. They think about it as a picture and a keyboard and a mouse. They're actually thinking about how they interact with the computer, like the point at where they actually get into the computer and see what the computer does. No one really cares, well, we do, but a lot of people don't really care about the guts of the machine anymore. They care about what they see. And this is what my research field and what I teach is about the human-computer interface, which is the area called human-computer interaction. So it's loosely defined everything that concerns how people interact with the computer, what they see, how they control the computer, this kind of thing. Everyone recognize what that is? It's a mouse. Yeah, we still use them, right? It's not just got a cord on the end. You don't usually have a cord anymore. So this is the first commercially successful mouse. If you know your computer science history, you know that the mouse was actually invented not quite 20 years earlier at Xerox, just the photocopier company. They didn't really pick up the ball on that one. But Apple popularized the mouse, and the mouse in particular to control a graphical user interface. And this changed computing completely for everyone. There's a great advertisement, which I usually show. I don't know why it's not in this talk. But when the Mac was first introduced, this original computer that had a mouse and a keyboard, there was this advertisement that said, and it was for Americans, it said, there are 290 million people in the United States, and only a fraction of those know how to use a computer. It's a pretty amazing statement. Like that's, what, 30 years ago? Only a fraction of the people could use a computer. Well, today, that's completely opposite. I mean, not only there's a lot more than about 280 million people in the United States, there's like 300 some, but only a fraction of the people there can't use a computer, right? And a lot of it is because of this human-computer interface. So let's go back at these these drawings. So I mean, you weren't drawing computers back in 1988, but you might draw, even a couple years ago, you probably would draw a computer, or maybe even today, something like this. It's a laptop. But a lot of people actually think even, this is a computer, right? Many of you have this in your pocket or in your bag, right? iPhone, Android, smartphone. That's a computer, obviously. What about this? Yes. Yeah. Wow. Yeah. Television supporters. So televisions do a lot more than just play shows, right? I mean, even just playing Netflix, I mean, that's a pretty complicated, there's a lot of processing going on. But you can also send and receive texts, right? You can use Skype, right? You can do, like a television is like a full computer. There's one thing that's starting to change here. Notice how when we went to the iPhone, it's kind of hard to carry around a mouse and a keyboard, right? So we moved to touch input because I can reach it. How well does touch input work with a television, right? I mean, there's a couple problems. Number one is I'm going to smear up my screen. Number two, I have to get up off the sofa. And one of the most amazing inventions for television was the remote control. And we don't want to break that, right? Like we've come a long way, baby, to get that. Let's not take that away. So we need some new way to interact with these kinds of things. What about this? Does everyone recognize this? Nest, right? Brand loyalty. Look at that. Well, I guess it's the only. So this is a smart thermostat. It's a pretty complicated computer. It's got Wi-Fi. It does a lot of calculations based on what it observes. It's got sensors. It's got a really neat bit of interaction where you twist the dial. Yeah, I'm not going to ask you what this is. It's a light. But you can actually buy Wi-Fi and internet-connected lights, right? So you can sit in the sofa and you can turn the light on or maybe make it a bit bluish if you're feeling kind of sad, or maybe a bit reddish if you want to be a little bit happy. What's happening is that what we think of as a computer interface, and maybe as a computer in whole, is moving way beyond the smartphone in your pocket, certainly way beyond the laptop or the giant PC under your desk. Your entire house or your entire world is becoming a computer. You've heard of the Internet of Things, right? So there's going to be stuff everywhere they're talking to each other, they're watching what we're doing. And we need to have, as humans, we need to have some kind of control over these things. Now, one way to control them is to sit down on my computer, boot up a website, but there'll come a point when if I just want to change something about my house because everything is wired to the internet, I need to communicate with it in some more immediate way. Touch might work in some cases, but in some cases, I need some other way to communicate. So here's one potential way. I'll just play you a little video. You probably recognize this guy.
We started with a sensor that can voice and movement to magic.
Xbox,
We thought this would be fun to play with. And it was. But something amazing is happening. The world is starting to imagine places we haven't thought. Unexpected things. Hopeful things. Beautiful things. Inspiring things. Which is why, even though the world keeps asking us what we'll do in the next, we're just as excited to ask the world the same thing.
Aren't you inspired? The music. So that's actually the old Kinect. That's a couple years old now. There's now a new Kinect, which is confusingly named Kinect 1. But the Kinect is a device that lets you control your television, play games. We can do a lot more than playing games. You can pick channels and things like that. And it does it entirely using computer vision. And it does a bit of audio processing too. But we're going to focus on the computer vision part of things. So it has two different cameras in it. It has an RGB camera, a color camera, and it has a depth sensing camera. And these things are always watching the people in the room. And they have a very sophisticated model. They understand a lot about what those people look like or what people look like and what they might be doing with their arms and their hands or maybe something else. And based on that, they can control the computer. So computer vision, in general, is this very broad class of computer science. There are many different interesting research problems, many interesting things that are applicable in many different environments. You've heard about virtual reality and so forth. But essentially, it boils down to this computers making some kind of intelligent decision about what they're watching or what is inside that, what they see in front of them. So a bit of, it was like showing some old black and white photos. This is an interesting one that computer vision essentially began with the United States Post Office. Not a very sort of sexy place to begin such a cool, Connect kind of thing. But so the original problem is that you'd get in the mail, you get a lot of letters like this, back when people used to send letters, and they would hand address them. And it would be very time intensive to have a whole room full of people reading all these letters and looking at the zip code, or in our case, the postal code, and deciding what bin or bucket to put it in, right? This took tons of time. And people used to write a lot of letters back then, right? Not so much now. So the United States Post Office said, hey, computers are getting, we can fit one in just a room, and they're only like $10 million. This is a great opportunity. Everything is, this is the future. We can use computers to actually read these zip codes, and eventually all around the world, other kinds of addresses, and we can actually, put people out of work, and save time, right? So we can be much more efficient, right? Like mail, I can get your mail delivered from cross coast in only like 7 days, as opposed to like 9, right? So this was and this happened in the 60s, and it took a couple more years, maybe in the mid-late 70s, they were actually running this kind of computer vision system. Seems like a good place to start, right? Like how hard can it be? Just read a couple numbers. Just read 5 numbers. Forget about, postal codes are actually a little bit harder. So part of the problem is that computer vision is actually, they call it like it's an unsolved problem. It's still very, very hard. Partly in this particular example, this original computer vision example, people don't write that neatly, right? I don't know about your handwriting. Mine is not that great because I'm always typing. So if we go down and we take, we can, as humans, we can look at these things and we can figure out, right? It's pretty clear what's a 7. Some of them are a little bit vague, but we can probably figure this out. For a computer, even today, this is actually quite difficult. And we know it's very difficult because you know what? We still use these kinds of examples to verify that you're not a computer. Have you ever seen one of these CAPTCHAs? I'm sure you have, right? You're posting to a blog or registering for PayPal or something like this. The way that we actually verify that you're not a computer is to give you this relatively simple computer vision problem, that was solved back in the 1970s, right? We basically give you some messy looking writing, and I have no idea what that says. Is it an S? I don't know. Could be a 9. Okay, same as like the morning group. You guys get so excited about CAPTCHAs. I didn't know, but so the thing is that our brains are awesome. Like we have great human vision systems. These kinds of systems are here to verify that we're a human. And did you know that, you see the number on the left, did you know that many of these CAPTCHA systems, you're actually doing some computer vision fact checking for people? So for Google, you're actually helping Google with Google Street View. So that 1293, that's a house number somewhere, I don't know where, and Google's taken a little picture. They've run their computer vision algorithm. They said, it looks kind of like 1293, but I'm not too sure. So they put it through in some of these CAPTCHAs, and then when you register for your PayPal account, you have to type 1293 plus whatever on earth that says, and then they get this verification. So again, another case just to show, so it's not like the talk ends here and computer vision doesn't work and we're all, but I'm going to show you some simple ways to do it, but understand that it's a hard problem. But you can do some very fun things with some pretty simple techniques. So I'm going to focus in this talk today about computer vision for human-computer interaction. So again, not just reading zip codes, but using computer vision to interact with a computer, to control a computer in some way, to provide input, much like the mouse and the keyboard in some ways. Now here I've got to get the lights down so you can see this next video. So this, if you watch closely, is a computer mouse. Did you know that a computer mouse has a camera inside? A tiny little camera, it's maybe like 16 pixels square. And here it's reading. You can see they've wired it up to an Arduino to actually get the camera signal out. And they're reading this 4-point font in this giant sheet of paper. So in fact, you're using computer vision all the time. Come on, lights. You're using computer vision whenever you use a mouse, most mice, because it's essentially just a camera. And the way it works is it sort of counts on the fact that your desk is a little bit dirty, or at least has texture. Dirt will work too. If your desk is completely shiny and clean and white, it's like being in a blizzard, right? There's no frame of reference, so the mouse doesn't know where it is. And it's because it's using a camera. So it needs a little specks of dirt or maybe textures to actually figure out where it is. So we use computer vision for human-computer interaction already. A more general case, sort of Kinect-like case, and is interesting, was originally pioneered by an artist. So Myron Kruger in the 1970s somehow got access to the giant computers of the day, taught himself programming, and did some of the earliest experiments with using computer vision to interact with a computer. And he did some pretty playful things. So here's some examples. He did work where you can actually control different shapes. You have to admit, this is in the late 70s, right? So just put your mind in that mode. And it'll track where people are. It has some understanding, you can see, of what a finger and a thumb is. This is no small feat. It understands what's foreground and background. It understands there's a person in front and nothing in the back. You can even do little interactive or multi-person input. It's almost Adobe Illustrator, right? It's just a couple more weeks, right? And you'd have the whole thing, right? But this one's really fun. So here they have this little sort of artificially intelligent critter with some very simple little rules. The critter always wants to climb to the top of the person. So again, like, it knows where the person is. The critter knows what the top is. And for some reason, this demo, they just constantly, it's a million ways to kill this critter. So they drop him down here. Poor guy tries to climb up again. They also have this notion of enclosure, right? A big part of computer vision is knowing, crush, right? What does this say about humanity? I don't know. So, okay. This is just crazy. Okay, so we'll skip that. So it's art. Yeah, no, I can point you to the link of the video. There's many more like that. The general idea is that this is the good thing is it was done in the late 1970s. Compared to the Kinect, it's relatively simple. Not quite as simple as what I'm going to show you here today, but it's in that ballpark. And it's basically looking at a camera and doing some understanding about the pixels. So let's do a very simple computer vision algorithm. So here you've seen this before. This is like pseudocode. So for each video frame, I'm going to identify some kind of special pixel. I'm being a bit vague. I'm going to be more precise in a moment, based on some kind of criteria. And I'm going to use that pixel's location to control the computer. This is the interaction part. So first, just so we're all on the same page, just want to totally verify that we know what we're talking about. So let's just, what is a video frame? Because here's some video. Every frame of a video is just a picture. It just changes a little bit every time, usually 30 times a second, maybe 60 if you've got a high frame rate. So I'm basically tracking back and forth. So in this picture, I've got a bunch of frames. So the frames just change a little, tiny bit each time, like so. And I can look at, because computers are not inherently smart, but boy, can they do things very quickly, right? So I'm getting video 30 times a second. It's not a lot. It's like 30 milliseconds, like every frame. And I go through, and the computer can look at all of those tiny little pixels and make some kind of decision based on that. But first, we should maybe just to verify we know what we're talking about, let's talk about a pixel for a second. So every image is composed of pixels. It's just a big grid of pixels. So I could pick one or pick a bunch of them and take a look. So here's a few here. I'm just going to zoom in. So the pixels are just a two-dimensional array or a matrix if you're into linear algebra. You could be a bit slick and say that. But essentially, it's a big grid of these pixels. And every pixel, if we look at one, what is it? Well, it basically has a location. So here, this pixel is at 270, 23. So I can identify this pixel and say that is the pixel at this location. So that's what we're talking about with pixels, just a bunch of little dots. When the dots are far enough away, then it looks pretty good. Okay, so we know what a frame is, we know what a pixel is. Let's expand this very vague, identify a special pixel based on some criteria. We can be a little bit more clear about this. Let's write another little algorithm. And you may have written algorithms like this in your computer science class. Array operations, find the largest element in an array, this kind of thing. This is what it is. In fact, this is what, honestly, 80% of the algorithms in the world are. Get a big list of things and go through and look at them one by one and decide something about them. So let's start out, like a lot of algorithms, with kind of a stupid but reasonable guess. I'm going to assume that my most special pixel is the one in the very top left corner in position 0, 0. It's probably a terrible guess, but I'm going to guess that that is the most special one. Then I'm going to go through, and for each pixel in that image, so I'm going to go through that entire grid. It's a lot of pixels. And I'm going to see if that pixel that I'm looking at is more special than the one that I picked already. So what do I mean by more special? Let's talk about this. In this case, we're going to say that more special means it's more pink. I don't know if you've noticed, but this building has a lot of pink. The Faculty of Mathematics, which is computer science, is part of it. The official color is pink. So there's a lot of pink around. So we just kind of embrace it, right? So hot pink. So what we want to do in this demo is we want to look at pixels, and we're going to see which one is pink. What is pink? Let's get philosophical for a second, right? What do I mean by pink? That's a little bit vague. We have to be very precise for computer algorithms. So we can take a dropper, we can look at a particular kind of pixel. The good thing is that every pixel has color, right, in this case. And there are different ways to represent color. You've probably seen RGB, red, green, blue. It's a very common way to represent color. It's not so great for humans. It's awesome for computers. We're going to look at a different color model called the hue, saturation, brightness model. So this models every color in degree. Do you remember the color wheel from art, right? It's like a big circle, so 360 degrees. So red is north and so forth. And then saturation and brightness are just some percentage, so really bright or really saturated color. So it's a really nice, this actually makes sense to humans. And the good thing is it's just a little bit of math to convert from RGB to HSB. It's the same color, it's just a different way of looking at it. But this will become convenient when we talk about what's pink. So let's look at a couple different pixels. So this one's 13 degrees hue, 31 degrees saturation, 48% brightness. Here's another one, very different hue, 336 degrees. This one's 352. So they all have these different numbers. So using these numbers, we can establish, we can do some kind of comparison. All we need to do is define pink. So here's how I'm going to define pink. This is pink for the purpose of this code. 330 degree hue and super bright and super saturated. So like hot, fully saturated pink. We can use this notion of what pink is to look at the distance between every single pixel I'm looking at, and I can go, well, how close it is to my ideal pink, this amazing pink that I've defined. And you can do that just by using an expanded version of Pythagorean's theorem, or Euclidean distance if you're into that. Basically, I have three values, right? I can square them, take the square root, and then of the entire sum, and I've got a measure of distance. Works pretty well. And by doing that, I can say that this muddy brown, the difference between that, or the distance between that muddy brown and my perfect pink is much greater than the distance between this kind of pinkish color and my perfect pink. So I can say that that one is more pink. And then I can run my algorithm, and I can go through and look at every single pixel. The black position is the one it thinks is the most pink, the most special. And it updates and keeps saying, like, oh, wow, this one's even more special. Oh, this is even more special. And it goes through the entire image, and it decides that this is the most special, most pink pixel in this case. It's just a particular image I took had a lot of pinkish pixels down in the bottom right. So this is what it does. It goes through and it does so that more pink really means how far is it away from the pink that I have decided is my perfect pink. So I can now use the most special pixels location to control the computer in some way. So, and what I mean by that for the purpose of this demo, I'm just going to move a graphical object. So let's take a look at a demo. Let me just switch out of this. So here, so I'm using processing. People know processing? You use that in your... Seriously? You don't? Please, someone, does anyone know the processing ID? You're kidding, because the other group, they totally were all over it. That's a weird, okay, you got to check into the, okay. It's basically Java with a really nice, nice graphics library in it, but it also does some computer vision demos pretty nicely. Okay, so here I am. You can see me. This particular, so right now, it's looking for some default color. I don't know what it is. It's looking very hard. But I'm going to teach it to look for a pink color. So I just clicked on the mouse to say this is what, let's go right up to the top. Well, I guess it really wants to get this bottom part. So I basically just taught it what is the most pink color. I think I can do this. So there I'm just in black and white, just so you can see. And now it's tracking the position of this bright pink marker based on that very simple algorithm I just showed you. It's already the connect. I just invented the connect right here. This is it. This is it. No, I mean, there's a bit. There's a little bit more engineering, but I mean, it's basically that's what it is. So, but this is a very simple. I hope none of the Connect engineers watch this video. So, okay, so yeah. So, they're like, well, we worked for 3 years on that. Okay, so I actually know the people that developed the Connect. So yeah, I'm sorry, Andy. Okay, so another very simple computer vision algorithm. Let's just change things a little bit, because that was pretty cool, but we can even do something more exciting and more interactive for everyone. Let's change our algorithm slightly to say for each video frame, I'm going to count these special pixels based on some criteria. So here's my criteria again. What I'm going to do is, this is another, you've probably seen this kind of algorithm before. I'm going to have some variable to keep a count. I'm going to go through a giant list. I'm going to see if it passes some criteria and add one onto that count. When I'm done, I can say like, hey, I found 100 of them. So here, I'm going to keep a count of how many pixels are pinkish, and I'm going to use that count of those special pixels to control the computer in some way. So it's just a small change, but otherwise exactly the same, distance from pink, all that kind of stuff. This time I'm just counting how many there are. So for this, I'm going to do another demo. Let's go back to processing. Remember how I said computers are super fast? Okay, there we are. Okay, so now I'm using a different camera here. This camera, or this program, knows a little bit about pink things. So it knows if I turn the color off for a second. So it says, oh, I know, that's totally pink. And that's totally yellow. In fact, it knows that that's yellow as well, because it's pretty close to the same yellow. And it can do something else that's pretty exciting. So I can teach it. I can say, so I'm going to teach it about yellow first. So here's my yellow. I'm going to tell it, like, this means no yellow. This is more yellow. And now, do you see that bar on the side? So that bar is telling me how much yellow there is. And it's more or less ignoring that thing in the back, right? It's going to start picking yours up if you're in the side. So now I can see, well, now it's got more yellow, less yellow. And I can do the same thing with my pink, right? I can say, this is a lot of pink, and this is no pink-ish. And now when I do this, let me just move the screen over. Right? Okay. So now we can do something interesting. So I'm going to do, oh no, I'll give you guys first. I'll do this side first. Yeah, don't worry. Okay, so we have to teach it something, because I just taught it for me holding up one card. We have to teach it about your cards, okay? Let me just do. Okay, everyone put your cards down. Everyone hold up hold up only your pink cards. Just for a second. Now the trick is that if you aim it too high, the light's gonna blow it out. So you want to find the right angle. And I'm just gonna try to teach it. So I'm gonna try to teach it about yours a little bit. I can do a little bit better. It's not bad. It's not. Okay. Okay, now everyone hide your pink cards so you can't see the pink cards. Okay, I'm going to teach it that's low. Okay. Now get out your yellow cards and hold them up. Let's just hold your yellow cards up for a second. I'm going to try to get. Okay, now hide your yellow cards. So can't see them, hide them, hide them. It's going to mess up if you don't hide them. No, seriously, hide them. It's going to, otherwise you basically won't be able to do anything. Okay, so now let's see if this will work. Now you're playing a game. So now put up your yellow cards. Moves to the left. Hide them, hide them, hide them. Put your pink cards up. You just got it, wow. So the trick is that you move to the right, you get stuck in the left. Use your yellow cards to go left, but you have to be organized. See, get that, and every time you get a treat, he smiles. Here's another one. I'll slow it down a bit. You've got to cooperate. Okay, I'm going to make it a little harder. Run, 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 run. That's it. Okay, don't worry. So what's your score? 9. 9. Let's see. Let's see. I have to get you out of the frame. Okay, so we have to train. It doesn't know a lot. It only knows about the colors on this side, so let's train it first. So, yellow first. So everyone hold your yellow cards up. Okay, so high. Okay, now hide your yellow cards. That's low. Okay, now we're going to train pink. So pink cards up. I know, there's 2 colors. Okay, so now hide all your pink cards. All right, now let's see. So I want to make it a little bit easier for you. I don't want to kill you on this game. All right. So get over. Oh, okay, you can do it. It's starting out a little bit hard. I can make it. Oh! Come on, Jan, come on! So everyone, pretty good, pretty good. Okay. We need a rematch, yeah. See, computer, very simple algorithm. I just told you how to do that, more or less, a couple little small details. It's kind of fun, you're interacting, you're doing it in a big crowd. And you know what else? It proves that high school students can cooperate, right? I mean, this is something that has people like, we just saw evidence today, right? So that's fantastic. Let's talk about a slightly more complex computer vision algorithm. I'm not going to give you the details, but it leads into some examples of work that I've done. So here, instead of looking at each individual pixel, I can look at, for each video frame, I can subtract out the background pixels, whatever that means. So I want to get rid of all the junk behind me. I want to just get stuff in front. I can look at all those pixels that are left, those ones that are in the foreground. I can look at, well, do they touch each other? And if they touch each other, I can call that a blob, kind of like a blob. So I have two people, it'll be two separate blobs. And they can use that blob position to control a computer. So I did something, I'm going to show you an example from my own research/art. So here's an example. This was done in an art gallery, had a very high ceiling, and I put a lot of infrared illuminators. So it's very common in these computer vision algorithms to use infrared light. We can't see it. And I can illuminate the room very bright. These are meant for parking lots, so they're super bright. Bought them legally off of a place in Alibaba. So turns out infrared illuminators have our import controls because they're considered military devices. But don't tell anyone, oh, it's being recorded. No, okay. And I had two cameras up in the ceiling. So I put these two cameras together, and then I can do this simple blob tracking. So that's the view of the ceiling, and I'm just walking back and forth. And it tracks a blob, which is just a person, so the person in their shadows. And then that pink position is just the topmost center pixel of that blob. And I did a little bit of filtering to get rid of some of those when I showed that colored demo of it jumping around. So why did I do this? So the reason, this is an interesting way to control a computer that's not a usual computer. So this was done in an art gallery, and the reason for the project is art galleries have very large collections. They often can't throw them all, they can't put them all on the wall. There's not enough space. Some things aren't light fast. Some things are out on loan even. They're often down in the basement. They've been scanning them, but the problem is, how do you get these scans of these artworks for people to see? Well, one is you could make a little app and people could look at it in their phone and have a database, but you lose this sort of museum art gallery experience. So I wanted to develop a system that allows people to still look at art in the same way or similar way, two-dimensional art, that they would in a gallery, but using this interactive system. So here's how the system worked. I'll just dim the lights again. So right now the camera's up in the ceiling. They're tracking each of these 4 different people. And each of them are controlling this computer, essentially behind them, this very large display, all written in processing, the front end. The back end is C++, something a little bit more heavy duty for vision. And it allows you to pick artworks in this sort of random way. So when you move your body around, each of those little stripes represents one artwork in the collection. It's just actually the mean color of that particular two-dimensional artwork. And then when you step forward, it pulls the artwork up onto the display. The interesting thing is you don't have a lot of control. That this is intentionally not a database. It basically has this serendipitous discovery. It's the same thing like when you go to an art gallery, you're not too sure what you want to see, and you kind of turn the corner and you find something interesting. This is the idea behind this. And then you can go up and get some kind of metadata, look at who the artist was, again, by tracking. And that very thin line is just the vision of that person. So very simple, very, very simple computer vision. The idea is that it rewards this or enforces this kind of contemplative, slow kind of way of looking at art. One problem, though. So here's some security camera footage of people using the system. You can see what they're doing. They're playing the Kinect, right? Like that's what they're doing. Everyone's used to this kind of gestural input that just walking around very slowly without using your hands, people aren't used to. So people really want to use their hands to control computers, mainly because they've seen that Kinect video I showed you just a moment ago. Or maybe because they've seen this. See if you remember this, or if you know about this film. So here's the future of interaction, right? Like, forget about the mouse and the keyboard. We're going to use gestures to control the computer. It's from Minority Report from the late 90s, I think, Tom Cruise. But you can see what he's doing. Like, he's basically using these different hand gestures up in front of his body. He's got special gloves on to make the tracking problem a little bit easier. You know, we could put pink fingers on and do something that I just showed you now. And he's doing these kinds of gestures to control a computer. So the one problem with this is it's tiring, right? So here's a research project of mine where we use this device called a Leap Motion, which maybe you've heard of. So they're usually on a desktop, so we strap two of them onto a person's thighs, and it allows them to use these kinds of whole body gestures, or these free space gestures, but do them in a more comfortable way, more comfortable manner. We had to do, and this is a computer vision system. A Leap Motion just has 2 cameras, infrared illuminators, and some computer vision algorithms. And you can do pretty precise kind of movements. So we have a special kind of cursor that shows you what the system is recognizing your fingers as doing, whether, you know, where your thumb is, which finger is out. So you can control different modes, like pointing. This is why we call this gunslinger, because it's got this kind of gun analogy, or looks a bit like a gun when they're using it. I can click on targets like this. And it also tells you when you're starting to lose tracking, or when you're starting to do something that you're moving your hand too far away. We wanted to enforce people to do this in a more comfortable way. So very not Tom Cruise Minority Report, but to do it in these very sort of subtle ways. Let's just bring our lights up for a sec so we can. So that's an example. So essentially, it's all computer vision algorithms. That's what's running the Leap. That's what we're using. And we're using it to interact with a computer. So just to sum up, so using computer vision, you know, video cameras can be used for human-computer interaction. That's what I'm trying to convince you of or tell you about today. There's 2 pieces. It's not just computer vision, but it's using them to interact as well. You can do interesting things with pretty simple algorithms in this field. Like, you can do, like, there are certainly boundaries to it, but you can get some fun effects doing it right away. You can do some really amazing things with more advanced computer vision algorithms. So if this is a reason, and there is a fair amount of math involved to do these more advanced, like you actually get to use, if you've learned about eigenvectors and eigenvalues, you actually use some of these to do these computer vision algorithms. Some of these things that seem very esoteric, this is where they become applied, which is what is interesting. So that's all I've got for you today. But here, if you want to take a look at some other projects that I've done, here's my website. I think there's a link on the CS4U page as well, so you can see some other art and research projects up there. And if you want to learn more, here's some recommendations, which I'm going to work with Barbara from CS4U to get this out to you some way. It's not in your packet, but if you haven't used processing, you're missing out, because it's a really great visual programming system. It's a great article. It gives you some code. And if you're really into the hardcore side of computer vision, you should start reading up on OpenCV using C++ or Python. That's where the really heavy lifting happens. So. Great. So that's the end of my talk. So, okay.